I need to spotlight you also.
It should be spotlighted. It's spotlighted already.
Okay.
Yeah. So. Okay, so yeah, I guess we can get started. Yeah, so this is the last lecture of the series. We're going to be finishing up the discussion and getting to generalized entropy today. Yeah, just for people joining on Zoom, just a reminder, I think we have the Q&A feature activated. So if you have a question, remember to type something into there, and either the moderators will ask your question for you, or they might ask you to unmute. Yeah, and so then before going into the lecture, I did want to just point out or acknowledge a couple people that have been helping a lot for this lecture series, just so the people online know. So we had Pranav Kulakot and Edward Broadberry, two students here who've been doing a lot of work on helping with the Zoom logistics and managing the questions and answers. So that's been really helpful to have someone dealing with that while I'm up here. So thanks a lot, guys. And then of course, thanks to Ted Jacobson for organizing the whole thing. And he's been dealing with a bunch of the logistics and stuff. And of course, thanks to the MCFP at University of Maryland for putting this all together. So yeah, so if you guys enjoyed the course, feel free to let those guys know that you appreciated it. Okay. Yeah, right before we get going on the stuff that we're doing now, I realized I watched the tape on the last one, and there was a question that I didn't understand what someone was asking, but I think I do now. So it's worth pointing out. There was a question about this equation that this modular operator psi acting on psi is 0. So this is always true of a modular operator. And it's just by definition. The question was, I think, when I re-listened to it, was how is this not in conflict with the fact that we assumed this vector to be separating, which was the statement that no operator in the algebra annihilates the state. The point is that this is separating for the specific algebra you're talking about, and this thing is not an element of the algebra. So it's okay for the modular operator to annihilate the state. It only needs to be separating for every operator in the algebra. So I thought it was worth pointing out, just to remember that it's not all operators can't annihilate this. It's just the ones in the algebra. Okay. Okay, so just to review where we got to last time. So the thing that we were doing was we had written down this proposed algebra that consisted of the gauge invariant operators for a subregion. It's generated by this Q-hat operator, which was this observer Hamiltonian, and then these dressed versions of the local quantum field theory operators. So you dress in a way that depends on the conjugate variable to this Hamiltonian. So P is like a time variable in an operator sense. So this was our proposed gravitational algebra. It takes the form of a cross product, which we discussed a bit yesterday. And then we said, okay, let's start doing this computation of modular operators on this algebra. So we considered this state that consisted of this KMS state that we defined the algebra for. So this is the quantum field theory state whose modular Hamiltonian is this H here. And then we tensored in a wave function for the additional observer degree of freedom we denoted by F. And the thing we found right at the end of last lecture is that the modular operator factorizes into an operator associated with this algebra, and then another piece that is affiliated with the commutant algebra, which I didn't rewrite here, because we probably won't need it now, but we showed that this thing really was an element of the commutant algebra. So in particular, so as we're going to show now, these factors in the modular operator have the interpretation of density matrices, and they take this following form. I've restored the factors of beta just because it'll be interesting to see where beta comes in. So remember, beta was equal to 2 pi over kappa. Kappa was the surface gravity associated with this boost vector field. And so in particular, the piece affiliated with the algebra, it's nice, it only depends on this Q hat operator, so it takes a fairly simple form. Okay, so the goal is to now show that this form, this factorization of the modular operator ensures that there's actually a trace defined on the algebra. And so that's what we're going to talk about right now. So the trace. This is not a good marker either. Okay, it's actually very simple. As soon as you see that your modular operator factorizes, you can immediately write down the following trace of a hat. This is an arbitrary element of the algebra. You just take the expectation value in this state psi hat of, you insert the inverse density matrix here. So you can think of this as roughly each of these states is like half of a density matrix, and then you divide out by the density matrix. So in this equation, it's like you're taking a trace over all states where you've gotten rid of the probability distribution of being in that state. So just because we have a lot to get to, I'm going to keep this as an exercise. You can verify the tracial property just using simple algebraic manipulations. So it's a b hat, according to this equation, equals trace of b hat a hat. You just want to use the delta psi hat acting on psi hat is equal to psi hat, so you can kind of put deltas in where you need it, and then you just use the fact that this factorizes into the product, and you use the fact that this rho prime really is affiliated with the commutant. So as an exercise, just play around with this equation. The other thing you want to remember is that psi hat, a hat, b hat, psi hat equals psi hat, b hat, delta psi. Sorry, I'm putting hats on everything, but just to remind you, the hats just mean you're in the cross product algebra. So if you put these pieces together, you'll be able to verify this identity in a couple lines. So I'll leave that as an exercise for you to get comfortable with that.
Is that row there with subscript psi has no hat?
Thank you. Yeah, it's that. It's this.
Yeah.
Okay. Okay, so one thing I want to point out is, so this will always give you a trace on your algebra. But the first thing that we can see is that we said we decomposed the modular operator into a product of two factors, and this decomposition is actually ambiguous. You can see that if I rescale both rho and rho prime, that's not going, by a constant, that's not going to affect the fact that their product, rescaling cancels out because this one's a rho and then this is an inverse. In fact, if the algebra had a center, you could rescale by anything in the center because you can't really associate the central operators to A or A prime. So for us, the algebra, I'm just going to tell you that it doesn't have a center, it's a factor, but there's still, you can still, well, the center is generated by the identity, so you can still rescale the density matrices. So what that means is, if you look at what happens in this equation, if I rescale the density matrix, all that does is rescales the trace. And so this is how we see this property, that the trace is only defined up to an overall constant rescaling. And so roughly by picking this normalization for beta, where for the density matrix here, I've picked a choice of that scaling for the trace. So one thing you can do in order to, if you're comparing different states, you want to make sure that you're using the same normalization for this trace. One way you can ensure that you normalize the trace correct or consistently across different states is to define the trace of some operator to have a fixed value. So what you can do is fix, say, some projection E hat, and just say, I'm gonna normalize the trace, whatever your favorite projection is here, such that trace of this thing, you need to make sure it's an operator that has finite trace. So pick any operator with finite trace and normalize it to be 1. So this normalization with the specific factors of 1 over beta in the density matrix comes from taking E hat equal to this step function, theta of Q hat. So this is, okay, it's equal to 1 for Q greater than 0, 0 for Q less than, say, equal, I don't know, to 0. It doesn't matter what it's doing right now, 0. So it's just the step function. And we picked this thing anticipating something that we're going to do later, where we're going to actually project the algebra down to a subspace generated by this projection. Okay, so another thing you can check is you can write down this trace and verify that the way we normalized the trace with this specific density matrix and the factors of beta, it's actually equal to 1. Roughly, let me show you, I can show you, so this is like psi f times beta e to the minus beta q, I think, right? Yeah. And basically there's 1 over f of q. So theta of q. 1 over f. This will be a star, but f of q. Psi f. None of these depend on the quantum field theory operators, so really you're just taking the expectation value of this overall operator. Well, you're doing this, you only have to worry about the L2 of R factors here. And so then you could show that this is just integral of this thing from minus infinity to infinity, theta of y. The f's cancel out here, and it's just beta e to the minus beta y. Okay. I'll let you do that integral and check that it's equal to 1. Okay, so that's just to say that we picked a normalization of the trace by making this thing have trace 1. So we're nearly to the point that we can actually diagnose the type of the algebra that we've constructed at this point. So first of all, we found a trace. Technically, you need to verify these other assumptions, these other requirements that it's faithful, semi-finite, normal. I'll just tell you that it does satisfy those requirements. So what that does, it says this algebra is not type 3, basically, because type 3 algebras were the ones that didn't have these traces on it. And so then we can check a few other things, like we want to see, we're left to type 1 or 2, and there's a sub-classification as well. So the first thing you can check is that on this algebra, trace of the identity is equal to infinity. It's roughly a similar calculation to that, but you don't cut the integral off here. You just put 1 there, and you can see that blows up. So that restricts us to either type 1 infinity or type 2 infinity. And the way you identify its type 2 is you just show that there's, a continuum of values that this trace can take. Instead of taking these, well, I could just take these theta functions, and instead of cutting it off at 1, I can do theta basically of q hat minus a. Just pick that a for all different values. You'll see you'll get a continuum of values for this trace just by shifting the lower limit of this integral here. Okay, so what this implies is that the algebra is type 2 infinity that we've constructed. And so this is a standard result in the theory of von Neumann algebras. We started with a type 3-1 quantum field theory algebra and took the cross product. That's just well known to be a type 2 infinity algebra. The one other interesting thing I want to point out with this result is that this is actually also a factor. So again, the center consists just of the operators proportional to the identity. And this is a consequence of the fact of starting with type 3, 1 in particular. So you get a factor from the cross product when you're doing these type 3, 1 algebras, which we said are kind of the relevant algebras in quantum field theory. So these other type 3 lambdas, you would still get these type 2 cross product algebras, but they would have central operators. And there's a whole important story for how people analyze that center when investigating the structure of type 3 algebras. But for us, we just say we know we're interested in quantum field theory, we're going to get a factor. Okay, so now we want to do something with the fact that we have identified this algebra as type 2. So the important thing about that statement really is that the algebra has a trace. And we want to take advantage of that to start investigating entropies. Now that we have a trace and density matrices, we can start doing, well, talking about entropies. I should have mentioned, by the way, once you've chosen a normalization for the trace, you always take the density matrices to have trace 1. So that's how you normalize density matrices going forward there. So the factors of 1 over beta were chosen so that those density matrices with this trace normalized like this have trace 1. Okay, so we're going to move on now to the main thing, which is generalized entropy. Actually, I think all of these are dying. I don't know if you can still see this, but if it's possible for someone to grab a dark marker, I don't just yeah, sorry about that. You can try maybe the not really better. I'll keep going with these, but yeah, let me know if it starts getting invisible. Okay, so we're going to start looking at states on this algebra and computing entropies. Let's consider the following state. It's going to look like the state we considered before, but instead of the quantum field theory, the KMS state psi, we're going to take an arbitrary state. We're going to take an arbitrary state phi for the quantum fields, and then we'll also take an arbitrary wave function for the observer part of the Hilbert space. So this doesn't have to be related to the one we were using before. So last time we did a fairly detailed calculation of the modular operators. One of the reasons I showed sort of some of the details there was I wanted to present the calculation in a way that actually generalizes quite easily to these. So instead of writing all of those out on the board, I'm going to show you the end result. There's just a few extra steps you have to throw in due to the fact that you're working with an arbitrary state phi as opposed to this vacuum state side that we took the cross product in. And so again, you compute this modular operator. Here, we'll call this phi hat. And again, it's factorizes. And this is the one that we're interested in, so I'll write that out now. So we're gonna, I'll explain these. So it's e to the IP h psi phi f of q hat minus h on. I should put the betas in actually. Sorry, just going through markers here. That one's much better. We'll use that one. Let me rewrite this. So, yeah, 1 over beta e to the I p hat H psi phi over beta. This is the relative modular Hamiltonian. Yeah. F of q hat minus H psi phi over beta, e to the beta q hat, delta phi for this state here. Basically then times the complex conjugate of everything. Phi over beta, e to the minus I p hat, H psi phi over beta, then we're done. Okay, it looks long. Really, when you do the modular, when you do the computation, you're essentially computing half of this. This is why the modular or the Tomita operators are a bit easier. So what does this consist of? This is the modular operator for the state phi. Modular operator, just for the quantum fields. And this H psi phi is again the relative modular Hamiltonian. So it's the relative modular Hamiltonian. It comes from this relative Tomita operator, which if you remember this S psi phi, A acting on state phi gives you A dagger acting on state psi. So it switches the state in addition to changing A to A dagger.
Is there an intuition for the relative modular Hamiltonian similar to the simple one for the modular Hamiltonian?
In terms of density matrices?
Yeah.
Yeah. I'm going to use that. Should I write it now or should I just bring it? So it's roughly, yeah, okay. H psi phi is morally minus log rho psi plus log rho phi prime. And this is actually just true. This is true in the type 1 and 2 case. So, and then H phi, for example, so is equal to minus log rho phi plus log rho phi prime. So it's like you just switch one of the density matrices of the modular operator. Okay, so now we have the density matrix. Once you have a density matrix, you can go ahead and start computing entropies. We'll write those formulas now. So the entropy is given by the usual von Neumann entropy formula. S of rho phi hat equals minus trace rho phi log rho phi hat. And it's actually simpler to just say this is the expectation value of minus log rho phi hat in the state phi hat. So minus log rho phi hat. Okay, so the main thing we have to do is compute the log of this density matrix and then take its expectation value. That'll give us an entropy. So let me write the formula just to show you so you can express this density matrix, the log, exactly as minus beta q hat minus H psi phi. Yeah, plus log beta. Minus log, okay, f of q hat, e to the minus, or e to the I p hat, psi phi over beta. It's going to look a little complicated for the moment. H psi phi over beta, and then f star q hat. Okay, so this is an exact expression, but then at the moment, we're going to have to do something because if you have any experience computing logs of operators, you know it gets a little complicated if things don't commute. So in particular, this operator doesn't commute with this operator, the P doesn't commute with the Q. So we have to think a little bit about how to take this log of this density matrix here. So for this, we're going to employ this semi-classical approximation. So what the approximation is we're going to take this wave function for the observer Hamiltonian to be slowly varying. So take f of y to be slowly varying. So equivalently, we can take the Fourier transform of, say, the momentum conjugate to that to be localized near zero in momentum. So this approximation is saying that if you think of this wave function as giving an uncertainty in the energy distribution, in particular, it's the energy distribution of this observer, but it just gives a certain uncertainty in energy. We're saying that we want everything to be very closely localized in time, in the sense that we're not smearing operators out, we're not coarse grading over time evolution. So roughly this P has the interpretation of time measured relative by the observer, and we're trying to take a limit right where there's not much uncertainty, so it's really well localized operators in time.
But conversely, that means it's not localized in its energy, the observer energy.
The observer energy is very widely spread out, yes.
Right, but then doesn't that mean the system energy is widely spread out?
Yeah, it's widely spread out. Of course, there's an order of limits where we were thinking, you know, where this came from was this G Newton to zero limit. And so it's widely spread out, but still somewhat suppressed relative to the G Newton limit. So there's sort of a happy medium order of limits that you can take where it's still small fluctuations of energy in terms of gravitational back reactions, but very broad fluctuations, you know, within that limit. So that's what the limit we're taking. So you can think of this F is really closely equal to the zero momentum eigenstate. It's not equal to it, this wouldn't be normalizable. So yeah, so just to mention that. What this limit does effectively is it also tends to decouple. It kind of, you can interpret it as saying that the observer is not very strongly entangled with the quantum fields. Roughly, if you remember, all of the quantum field operators had this twirling factor that involved these momenta. And so essentially this basically generates entanglement between the quantum field operators and the observer, because they would act on some states by F, and it shifts these in modular time in a way that depends on the observer's P value, so its time. So in this limit, we're saying that this effect of twirling the operators is very suppressed, and so they're essentially decoupled, well, unentangled. So of course, this state looks unentangled when we write it down, but you have to remember that the quantum field theory operators really are these twirled things. So really, this state does describe entanglement between the quantum fields and the observer.
So to get the approximation that you want, you said you wanted F slowly varying.
Yes.
And then you mentioned, like, as a side effect of that, there's little entanglement with the observer. But is it also the case that you could have started saying there better not be any entanglement, strong entanglement with the observer for some other reason? Or like, what's the primary driver of the approximation?
So we'll see at the end of the day, it allows us to separate the observer's contribution to the generalized entropy from the quantum field contribution. It's a little hard to think about what that would be if those guys are not really independent systems.
Right, but you need that not for the approximation, but just sort of for the interpretation of the entropy.
It'll be part of the interpretation. It also, just to say, the formulas are a lot more complicated. They'll probably appear in some upcoming work, what happens when you don't take this approximation, but so that's something upcoming, but yeah, it is quite a bit harder calculation, I would say. So it's also just a matter of simplicity. Just we're trying to see if this is giving the right answer in this limit, basically. Okay. So let me tell you what this effectively does. Roughly, it makes any contributions from this p variable be suppressed. At the end of the day, when we take this expectation value, any factors of, I could expand this out as a power series in p. Those p's will always eventually hit a wave function f. And every time the p hits a wave function, it drops you down by a derivative of f, which we said are very small. So effectively what it lets us do is take this part of the operator and approximate it by its p equals 0 part of the expansion. So we're going to replace this just with delta phi. And as I said, you can justify this when you do the full calculation, but so what this does, so we'll just do that. So now delta phi, all that's left is delta phi and this observer wave function that depends on q. Those things commute, so we can just take the log as if they were C numbers. So what's the end result? We're going to say log rho phi hat is approximately equal to h psi phi. Then we get an h phi coming from the modular operator here. And then everything else that we had before. We also get the logs of the wave function here. And log beta is a constant, but that comes out in front. So we're going to take the expectation value of this operator here. And I want to write up the different terms because they each have a different interpretation. Okay, so the first term that we have is this expectation value of minus h psi phi plus h phi. Okay, the wave function for the observer just passes through, and so you're left with the expectation value of this operator just in the state phi. H phi drops out because it annihilates phi. So you're just left with the expectation value of this relative modular operator. Let me just write that. Which, if you remember from the second lecture on modular theory, this is the sort of Iraqi definition of the relative entropy between these two quantum field theory states. So S rel of phi with respect to psi. And we'll come back to this formula using that density matrix interpretation of the relative entropy in a little bit. But just for now, just remember this is this well-defined, and it should come with a minus sign, yeah. Well-defined relative entropy. The second term comes from the beta q hat. So we have, since it doesn't depend on the quantum fields, we can just take its expectation value in the state F. So q hat, remember, was this observer Hamiltonian. So this is just minus beta times the expectation value of the observer Hamiltonian. We can say in the state phi hat. The final term is the one involving the log of the observer wave function. Let's just be explicit. This is equal to minus integral. Everything just depends on q, so we just do this in the position basis. We'll call that y. Norm f of y squared log norm f of y squared. So this is sort of, if f was a continuum f squared is a continuum probability distribution. This is just the entropy of that probability distribution. So we assign this to be the entropy of the state F for the observer, associated with the uncertainty in their energy in this case, or well, just the uncertainty associated to their wave function. So at the end of the day, we have this semi-classical formula for the entropy of this state, it's minus the relative entropy minus expectation value of the observer Hamiltonian plus the entropy of the observer plus a constant log beta. And again, this choice of log beta kind of, just to remind you, the beta was chosen to normalize the density matrix. This is the piece that depends on that ambiguity in the normalization of the trace. So if I pick a different normalization, you're going to shift this basically by a constant. So this is maybe the first point, is that these entropies in these type 2 algebras, because of the non-canonical normalization of the trace, are really only defined up to constant shifts. And in some sense, this is more akin to entropies in a classical system, where you really only can make sense of entropy differences. And it also reflects the fact that you don't really have a microstate interpretation of this entropy. So this semi-classical approximation that we've taken, not just that slowly varying, more the small g Newton, and as well as the assumption that these observer energy eigenvalues, where you couldn't resolve discrete individual eigenstates, but we sort of coarse-grained over those as well, leads to this more continuum type entropy. So you don't quite have a state counting interpretation for these entropies. And that's just something that happens for type 2 algebras in general. Okay, the second thing is what this formula demonstrates at this point is that it's really written in terms of manifestly finite things. So the relative entropy is finite, at least if the states phi and psi are close enough to each other in quantum field theory. In particular, it's not a UV divergent. If the relative entropy blows up, I mean, it can blow up for ordinary quantum mechanics as well. It just means the states are, in some sense, perfectly distinguishable. But this is a UV finite quantity, and all of these things are UV finite as well. So kind of an important question that comes up at this point is that you can ask, like, where did the divergence in the entropy go? So in quantum field theories, we talked a lot about how entropies are not really well defined. They suffer from UV divergences. And you could just ask, how did we get rid of that UV divergence here? So the first point is related to this smearing in time. So in some sense, the fact that all of the operators, either the IP hat H, A, either the minus IP hat H, we've taken all of the quantum field theory operators and we've done this coarse grading involving a little bit of time evolution. The precise amount of time evolution really depends on this choice of the wave function for the observer. So once I tell you what the wave function for the observer is, then I know how much the operators are coarse grained in time. But the only one that doesn't coarse grain in time is this zero momentum eigenstate. And this is not a normalizable state in our algebra. So for all normalizable states, there's some coarse graining in time. And that seems to be behind why, at the end of the day, you're getting a finite answer. You could ask, how do you get back to the continuum quantum field theory description? Well, in that description, you want to go away from this coarse graining in time. You really want to be in this zero momentum eigenstate. So in that limit, I want to take the wave function for the observer in the energy space to be exactly constant. So I want a constant wave function. And you can see in that limit that this formula will blow up. And essentially, the issue is right here. So if I take this wave function to be exactly constant, I'm going to find a divergence in the entropy of the observer. So independently of the gravity description, you could say, how does the cross product regulate the entropy? Well, it does regulate it due to this smearing in time, and the divergence basically shows up here. If you want to get back the continuum description, you take F to be constant and you'll see the entropy blows up, as you would expect for quantum field theory entropy.
So that sounds good, but
Yeah, okay.
but is it the same divergence?
The area divergence?
Yeah. I mean,
let's come back to that when we go get the generalized entropy. So yeah, we need to try to argue that it would show up there. So let's wait until we write down the generalized entropy formula. So to try to get to Ted's question, let's go a bit further. So all I've done is shown you an entropy formula. The real thing we're interested in gravity is that to see if this has anything to do with the generalized entropy, which is supposed to be its own, UV finite quantity that describes the entropy of a subsystem in gravity. Okay, generalized entropy is already written there. So how do we turn this into a generalized entropy formula? So the first thing to remember is that the generalized entropy involves actually separately UV divergent terms. So remember the S gen was like A over 4G plus S QFT. This is divergent, and then we argued way at the beginning or stated that there's arguments that says this is divergent and this operator by itself is also separately divergent, and it's supposed to cancel between those terms. So in order to even try to match this formula, we need to do something where we kind of find, these separate UV divergent terms. And what we're going to do in order to do that is to start splitting the relative entropy into separately UV divergent terms, but writing it as this free energy expression. So since we're doing the relative entropy with respect to the state psi, we're going to consider the quantum field theory one-sided density matrix, which again is this UV divergent thing. But, since psi is thermal, it morally should be e to the minus beta HS, where this is the one-sided Hamiltonian. So we had like a subregion S, we have some boost vector, and we're just taking the part of the Hamiltonian coming from this and setting the vector to be 0 on the outside. That's what this one-sided thing is. And so the fact that the state's thermal with respect to it means that you can write it like a Gibbs state here. Now, this formula, so this relative entropy, it's nicest to do it in terms of these operators. So this H psi phi minus H phi is log, minus log rho psi plus log rho phi prime plus log rho phi minus log rho phi prime. So I've taken each of these guys and written them in terms of the two split density matrices for the quantum fields. Okay, and you can see that the rho phi prime density matrix shows up and cancels here. And so this is just difference in the log of the two one-sided density matrices here. And so using this expression, SREL psi phi equals expectation value in phi of H psi phi minus H phi. So now we're going to assume there's some sort of formal trace, regulated trace defined on the quantum field theory to write this as trace rho phi log rho phi minus rho phi log H psi, which is this density matrix here. So minus beta H psi. That should be plus. Okay, the way the minus signs work out. So this is the free energy expression. This is minus the QFT entropy of the quantum fields plus beta times the one-sided energy evaluated in the state phi plus log z plus a constant. So again, this is the statement that the relative entropy has this interpretation as a free energy difference when you're taking the relative entropy with respect to a Gibbs state. So it's a free energy with respect to the one-sided modular Hamiltonian in this case. Okay, so now we're gonna rewrite this formula here, using this split.
Just to be clear, what's happening here is you're pretending that there's a density matrix.
Yeah, so I pretended for just the quantum field degrees of freedom that I can take its own, its modular operator and split it into two density matrices in this way that would work if the algebra was type 1 or 2.
And you're just using that on a path to identify.
Yeah, because I'm trying to interpret that entropy formula I just erased, and this is what people do in quantum field theory, is they do compute the one-sided density matrices. They have some regulator prescription in mind. So we're assuming that we've done that and writing down what these formulas would translate to in that description. Okay, so the entropy that I erased, I'll write the new version now. Once you plug in this new expression for that minus relative entropy, it's now equal to minus beta of HS, the one-sided Hamiltonian, plus H observer. That one was already there in the state pi hat. And now we get this quantum field theory entropy. Remember, it was minus the relative entropy that appeared. So we get plus. Was there a question? Or
I forgot to move the camera.
oh, thanks. Yeah, sorry. Okay, just to restate online. So the entropy, we're just plugging in this formula for the relative entropy. When you go through and make the replacement, you get this one-sided energy. The observer energy was already there. We're evaluating expectation value in state pi. We get this Q of T entropy coming from the relative entropy term, and the minus sign is because we had minus relative entropy there. We already had the observer entropy. And then we have these constant terms that are going to go along for the ride. Log z is probably some divergent constant as well. So, okay, we're getting really close. We see we have an entropy here. So the final step is to apply this local Smarr formula, or local first law, as I called it in our paper. So we'll call it here since. Okay, yeah. We're supposed to call this the local Smarr formula.
Blame it on me.
Yeah, because Ted asked for it. Yeah, so what that formula said was this A over 4G is equal to minus beta HS plus H observer. And this was coming from applying subregion constraints. So now you should be able to see we're basically there. So using that to replace these observer Hamiltonian piece, we get that the entropy is equal to A over 4G expectation value in state phi hat plus S by UFT plus SF observer plus a constant coming from that. Okay, so this is the big result. So here we get A over 4G plus the quantum field theory entropy plus the observer entropy. The whole thing has the interpretation of a generalized entropy. Okay, so just to remind people where various parts went into this, the statement about the cancellation of the two divergence pieces here, we see it's kind of coming from this local subregion constraint. So, this thing was set up so that the divergences cancel between it's partially comes from here, that this entropy and this this one-sided energy is set up to cancel because that's just a relative entropy. The constraints say that that divergence here is going to match the divergence in the area because you want the constraints at the end of the day to be zero. So that's how you tie this divergence to the area divergence. And so that aspect of the cancellation of divergences comes from there. But ultimately, this expression being UV finite came from these global constraints. So we came from the fact we did this cross product it resulted in these smearing operators, or coarse graining, I should say, the operators in time. And that seemed to be behind the original formula's UV finiteness. So Ted's question was, how do you see that the observer entropy is the the divergence you want? Well, okay, I don't know. It's not obvious, I guess, from here, but you can get, yeah. I don't know if I have something specific to say on that. Maybe, yeah.
Right, it seems like maybe that's not quite, I mean, I understand that the entropy does diverge if you take that limit of the completely flat observer state in energy, but it seems like that's sort of independent of whether or not the divergences in the area term and the QFT term are canceling. And I'm not sure how to identify.
Yeah,
that.
so this is always ends up being, I mean, probably at the end of the day, the fact that this operator here is sort of a well-defined operator as part of it, because if you put this on the other side, the constraints are saying that it's saying that this is not a good operator by itself, but neither is this, but this basically the sum of the two are the observer Hamiltonian. So it's somehow tied to the fact that the observer Hamiltonian really, when you apply these constraints, plays the role of a regulated area operator. It's regulated by bulk energy of quantum fields. It doesn't immediately come to this, but I do know that there is, you can get the divergence in terms of, if you just view this as a regulator for the entropy, this would be the place you would see the divergence in the limit that you take the regulator to 0.
Right, but
Yeah.
that's the divergence in the generalized entropy.
Yeah, the other place that there's a divergence is this constant piece. So this cancellation that we've shown here, this is probably an important point as well, saying that the constraints are satisfied means basically the divergence in these quantities is the same as the divergence in the vacuum. So it says in an excited state, the divergences will cancel, assuming that, you know, this log z, for example, is probably a divergent thing. So assuming that you cancel the divergences in the background state, then it'll continue to cancel. And so those things are harder to access from these algebraic things. Those are, and this background value of the entropy. So it's related to, what is the meaning of this formula? I wrote A over 4G. Really, this constant piece also involves the background value of the area, because I'm setting G to 0. So really, this is the fluctuation. The finite thing would be that I should write this as A minus like A0, such that the overall thing divided by G is finite. And so there's a lot in this constant piece that's essentially inaccessible from just this cross product construction. You have to do other things, maybe consider, well, we might talk a little bit about that, but you have to consider other things to start thinking about this constant piece. And a lot of like the Euclidean path integral derivations are much more effective at getting at this constant piece.
There are a few questions on Zoom.
Okay, yeah, here's now's a good time.
Firstly, somebody asked when the area was promoted to an operator.
It was it's when we go to the quantum theory. So the area is not, it's a bit singular as an operator, but basically we did this classical first law, and then we said, okay, you have to interpret all of those terms in that equation now just as operators. Also, the local constraint you think of as an operator on some kinematical space, and then when you apply, when the constraint is 0, it says that this operator matches this. And so, yeah.
And then Luca asked for intuition, what would happen if we removed the observer to the box equation?
If you removed the observer, so say, yeah, so this is a good question, and it's maybe something to talk about. It's like if you try to impose these constraints without adding this extra observer, you're looking for things that are invariant. I think the analog would be you would look for operators in the quantum field theory that are invariant under the modular flow of some state. In the de Sitter case, in situations where you have a killing vector, I think people have rigorously shown that there are no operators that exactly commute with modular flow. On the other hand, there could in other states be operators that commute with modular flow, and so I would say, yeah, maybe it's sort of a discussion point of whether that's a consistent thing to do. Can you either remove the observer or construct it intrinsically from the degrees of freedom that are already there?
Can I ask you, yeah, on that point you just made about de Sitter space?
Yeah.
You said it's rigorously shown. Is it shown at the level of like perturbatively, but it might be not true non-perturbatively, or is it?
At
shown-
the level of quantum fields in a de Sitter background.
Exactly, so
Yes.
if you allow the geometry to be significantly modified also, is it possible that you then do have plenty of observables?
So are you saying you want to allow, there's a question of, are you just considering a different background, or are you allowing perturbations that back react, basically?
The latter.
So I would say if you do the perturbations that back react, depending on how you handle that, this possibly the whole setup I've described is going to not be a good language. So if it's sort of small back reaction, perhaps you can set it up in terms of a formal power series in G Newton and still make sense of at least some of the entropy formulas. But I think if you're really at finite G Newton, it's difficult to actually say, you know, have even a quantum field theory description, because in some sense you're doing non-perturbative quantum gravity.
Right, I just want to make
yeah.
it clear whether it's the absence of observables in that case without an observer, separate observer.
Mhm.
Is it a limitation of our like ability to analyze the system? Or is it some physical statement that, you know, quantum gravity has no observables in a compact region?
So it's probably more closely related to the latter. It's quite possible that, you know, subregions are not well defined non-perturbatively in gravity, or you have to work a lot harder to say what you mean by subregions non-perturbatively in quantum gravity. At least these localized ones that really, you know, we have examples in holography, like where you do these Ryuta-Miyagi things, and those you think have a good interpretation in principle at finite n, although really the geometric picture at finite n, it's much less clear. You should think of, in some sense, there's not a really geometric picture, things are very fuzzy at short distances, there might be strings, etc. So
I see, yeah, I think you just clarified, because I was kind of confusing the case of, let's say, a compact universe with the case of a subregion. So your point is that even to talk about a subregion, you're already not in full quantum gravity.
yeah, it's much more difficult to understand what that would mean in like a full quantum gravity description. So we really are trying to use aspects of the semiclassical limit, which, you know, I think it's interesting that you still get finite answers for the entropy even in these semiclassical type setups. How are we doing? Okay.
And there's one more question. Steve says, are you saying that at least in this formalism, the observer cannot be thought of as being made of quantum fields? And how does this make physical sense?
I'm saying the way I set it up, the observer wasn't made of quantum fields, and I'd say it's a question. I don't think that it's fundamentally limited in that way, though. I think there's probably room to try to actually, I would say one of the big questions is how should you actually model the observer? And I think in principle, it should be possible to do it intrinsically with the quantum fields. Okay.
But wait, but why doesn't that contradict what you just said about
the perturbative quantum fields? Just
Right.
the quantum fields on a fixed background.
Right, but then why doesn't that contradict the claim that for the de Sitter case where there's a killing vector?
Yeah, but it absolutely doesn't work in that case. Well, the algebra you get by doing this is nothing. When you average operators over all time in the de Sitter static patch, I think you can just show that there is no algebra.
So basically,
So I don't know. So in that
there
case,
it's just kind of a glitch due to the extra symmetry of the background.
yeah, I'm not sure in general how generic, whether that's the generic case or if generically you do have a good set of operators that are invariant. It's an interesting question, basically. So I don't think there's a definitive answer that I know of either way, but yeah. Yeah, sorry. Yeah, hopefully that answers Steve's question. I think he said, just can you use the quantum fields? And answer is, yeah, probably that's probably something people should work on. Okay. I'm gonna try to go quickly through this next part, although it might be one of the more interesting things. I wanted to talk about these positive energy conditions because there's some interesting implications for the algebras. Okay. So to this point, this generalized entropy formula works as long as you have this cross product set up. I think I mentioned a while ago that eventually we wanted to give the observer positive energy. And so you're always going to be able to define a formula like this. Really, all the positive energy condition does is it essentially restricts the states that you're working with. So to explain that statement, you can implement this positive energy condition by doing a projection just to the positive part of the observer spectrum. So this theta operator that we talked about before, this is an operator in my subregion algebra. So I can consider basically the positive energy projected algebra. I'll call it A pi. Yeah, I'll call it A pi hat, which is just pi times A times pi. So you just sandwich every operator with a projection. This is a subalgebra of the original cross product thing, and you have this act on a projection Hilbert space H pi, which is just this projection acting on the original Hilbert space. That was this quantum field theory and observer Hilbert space. Okay, so the statement is you can just do that, restrict to this subalgebra. And similarly, if you're worried about the commutant region, we set this up so that the commutant region extends out to infinity. So you might say, actually, I want to do positive ADM energy as well. You can do that with a projection as well. This is an element of the commutant. And I mentioned at some point that, did I get the betas here? H psi over beta, yeah. This operator here acts as the ADM Hamiltonian in this setup. So again, we can further project, so act with pi ADM on the commutant and on the Hilbert space as well. So yeah, let me just write an equation. So H pi is pi ADM, pi O observer acting on the kinematical Hilbert space. Okay, so that's how you get these positive energy projections. By acting on the Hilbert space, you ensure that this is your subregion algebra and its commutant is the projected algebra for the commutant algebra. So what is the effect of this? The interesting thing is that this changes the type of the subregion algebra. So if you now, basically what happens is when you project, this operator acts as the identity in the projected algebra. The trace still basically descends directly to the projected algebra. So in this case, we have trace of the identity, which was before just trace of this. We define this to be 1. So what that means is that this projected algebra is type 2, 1, which we encountered this in the first lecture, but it's basically a type 2 algebra that has a maximal value for the trace, and the maximal value is for the state whose density matrix is the identity. We mentioned before that a state with the density matrix equal to the identity is a maximal entropy state. So really what this set of things means is that in this projected algebra, there is a maximal entropy state.
Sorry, could you explain a trivial thing again? Why is the trace of the identity 1 only after you make this projection? I thought we defined it to be 1 before.
So really I said this operator acts as the identity in the projected algebra because you've sandwiched everything with pi. So this is in the projected algebra. I'm saying this is the trace of the identity in the projected algebra is equal to the trace of this in the other algebra before. So it's just that this thing had finite trace to begin with. We normalized it so it's 1.
Oh, that's right.
Yeah.
Thank
Yeah.
you.
Okay, so this is actually just an interesting statement. In the CLPW paper, they originally pointed out that this comes about from the use of projections. And they interpreted it as de Sitter having a maximal entropy state, which had been argued from various other thermodynamic and entropic reasonings prior to that. So you see it coming out of this algebraic formalism. If you evaluate the trace of this guy, because of the way various signs work out, you actually find that the algebra for the outside region, so this A hat pi prime, anyways, that's the algebra that is for the region. You just draw a picture. We have S is the local algebra, and then S prime extends out to infinity. This algebra remains type 2 infinity, because this thing has infinite trace when you work out what it is. It's not so hard to see. It's basically this, when you take the trace, this h psi, you're taking expectation value in the state psi, so this thing drops out. So it's just like the trace of this, but you did a minus sign, so you're integrating in the other direction. So yeah, that minus sign is crucial for getting type 2 infinity. And so this thing doesn't have a maximal entropy state. And so physically, how I interpret that is, in some sense, this subregion is approximately finite dimensional. I don't know, it has a maximal entropy state. It's sort of a localized subregion in full quantum gravity. I don't want to say something too strong, but you do think of sort of the entropy of subregions as maybe being, in some sense, finite dimensional. On the other hand, here we have like an infinite amount of space going out to infinity. So if you think of this as being tiled by little local subregions, even if each individually had a maximal entropy state, it's sort of, you don't have that going all the way out to infinity. Eventually you kind of approach some sort of vacuum state. So, okay, it's an interesting interpretation of that.
And if space is compact and you had a second observer outside in the complementary region.
Yeah, so this was considered in the CLPW paper. The way the signs work out is that there's a plus here. So the complementary algebra is type 2-1 in that case. Yes, so yeah, at least supports that general intuitive idea there. Okay, so in light of time, I wanted to have a little time to summarize. I'll just say, okay, there is this maximal entropy state. You can work out the wave function. It looks basically like, well, I can show you the wave function at least. It looks like it's basically a Boltzmann distribution for this observer energy. So this psi max looks like this KMS state, and then it's, okay, something like e to the minus beta Q over 2 or something. So it looks like a Boltzmann distribution for the observer, and then it's cut off at 0. The last thing I'll say is one of the reasons I was interested in these topics is when I was a grad student, I worked on this entanglement equilibrium conjecture that Ted was working on at the time. And that stated that he was considering small causal diamonds in semiclassical quantum gravity, and the conjecture was that those should have a maximal entropy state. And so basically, this is an algebraic way of maybe justifying that, or at least seeing how to treat that conjecture in an algebraic framework. So this relates to the entanglement equilibrium. That small causal diamonds have a max entropy state in semiclassical quantum gravity. So I think one possible application of some of this formalism is to maybe try to work out certain puzzles that come up with that when you're trying to go beyond a leading order and perturbation theory.
Can I ask you to say one more word about that? That maximal entropy, hypothesis was at fixed volume for the small diamond.
At fixed volume.
Can you remind us where that restriction enters the algebraic formulation?
Yeah, I think, yeah, that came from this, it came from the details of how we were fixing, the subregion, so we said that we wanted to fix this first order part of this. Unfortunately, this was a lot of notation, or the subregion. There's this first order contribution, so the piece linear in the graviton perturbation to this subregion, one-sided subregion Hamiltonian. So the thing generating the time translation in the subregion. In the case of a causal diamond, this is equal to the perturbation of the volume. And so we said that it seemed like a useful and possibly necessary gauge condition for the setup to fix this to be 0. And so that relates to the fixed volume.
And if you hadn't set it to 0, would there be another, would you not get the conclusion that the maximum entropy state?
Yeah, so, well, I'm not sure. At the end of the day, the max entropy state actually came from a completely different location, right? This observer Hamiltonian. So yeah, so depending on what exactly it means or how you translate the details between this setup and that, in particular, what this observer is supposed to mean, yeah, it would clarify that question. So I'm not sure, but yeah. Okay, we're close to being done. I mean, okay, so this was the main content of like the features of the construction I wanted to show. I think maybe, well, one thing I like to review is just to go over some kind of the inputs that went into arriving at a generalized entropy formula. Just because they focus at least one set of, well, one line of like future research is just trying to understand if the steps are justified or if you can make them better or see if the thing breaks down. So just to remind you some of the assumptions that went into this. So this assumption A1 is that these local quantum field theory algebras that were defined on the background can be defined, that they're type 3-1. And I would call this QFT in curved
Sorry, I think the
spacetime.
camera is still pointing in the right board.
There's quite a bit that goes into this construction. We just assume, or this assumption, we just assumed it, but there's a lot of details on how exactly you define the algebra, especially when there's gauge symmetry present. Also, yeah, we should split the video. Sorry.
Yeah. Okay.
Yeah, so this quantum field theory and curved space-time assumption. And so there's lots of things you can think about in terms of dressing and how exactly you construct these algebras. Second assumption is the observer / ADM degree of freedom. So there's already been a bunch of discussion, but this is something that I think is worth clarifying better. Can you give a more accurate model of the observer? Can you give it from an intrinsic description in terms of the quantum fields? What is the exact interpretation? Can you do maybe an explicit construction of this in holography, where some of the original ideas came from? They often say that it's somehow related to a choice of code subspace, or maybe some feature of the background geometry can define this. And I should point out, just because it's something I've worked on as well, is that there's a kind of, if you just take the observer as just an extra thing you add, it's very closely related to how edge modes work in semi-classical gravity. So this idea, at least in classical gravity, you see like phase spaces don't factorize just due to gauge symmetry, and you add extra degrees of freedom with edge modes. The whole procedure of adding the edge modes and then taking sort of a quotient where you impose the constraints is pretty closely analogous to how we arrived at this cross product algebra. So I think there's some people who have been thinking a bit about that connection as well. So the third assumption is this gravitational constraint. This was this C of C, this was the boost constraint. This is how we got the cross product algebra when we imposed the constraint on these two independent kinematical algebras. So there's questions here. So we imposed one constraint and we got this nice algebra that was giving regulated entropies. Of course, you could imagine there's a full set of diff constraints. So there's a question of how many of those were handled by a addressing procedure. Are there more constraints you should impose? It's kind of clear that it ties into what the observer is as well, that at the very least, at least in the de Sitter case, you see there's this rotation symmetry as well. You probably should impose a constraint on that and give the observer extra degrees of freedom to measure the frame. So there's a question of just how many other constraints should you impose. And then assumption A4 was this geometric modular flow. ULAR. This was the statement that this boost generator that shows up in the constraint actually corresponds to the modular flow of some state for the quantum fields. And so we gave some arguments for that. This is an interesting question just because it relates to certain expectations people have about how modular flows work, that they should look like a boost near an entangling surface. And there's all sorts of ways to approach this without necessarily doing any kind of quantum gravity. It's sort of a purely quantum field theory question. So you could try to maybe make it a precise conjecture there, try to prove it just in the context of quantum field theory. There's also, you could ask about how to characterize the precise features of the flow. In particular, we talked about this zeroth law. I should just mention part of this is the zeroth law, that kappa was constant. So that's one thing you would like to check, try to prove it or disprove it. And if it's not true, you should try to see if there's a correction. If the whole story goes through, does it lead to corrections to the entropy at the end of the day? So that's an interesting set of questions. So these four ingredients were what we used to arrive at this cross product algebra and to get a finite entropy. So that's what these four do for you. And so, yeah. So there's two more things that you add on top of this that relate to getting generalized entropy. Well, okay, there's actually just one more step. So the fifth step was the local Smarr formula that relates the area in the subregion to the energy of the observer and the local quantum field energy. So this step was specifically needed to convert our well-defined type 2 entropy into an expression that involves the generalized entropy in terms of an area and a quantum field theory entropy. And this one's kind of interesting. It's from the perspective of these kinds of relations where you would set like the entropy of an algebra to the generalized entropy. It also shows up in particular in these holographic derivations of Einstein's equations from entanglement. And so you can try to do similar things here. If you say, I have an algebraic entropy, which is this type 2 entropy, and I want to set it equal to the generalized entropy, it better be that my Einstein equations, the local constraints, are holding in the subregion. So this is the piece that really ties things to the geometry. The final one was were these positive energy projections. The only thing this does for you is in the local case is what results in the type 2-1 algebra. So you can do everything else independent of this and still get these type 2 algebras with well-defined entropies. So this is one that's possibly one of the weak points, maybe. There might be situations that this positive energy projection on this observer, if you appropriately interpret how the observer works, that you shouldn't do this. For example, I mean, there's one case that you don't do this, is when you do this construction, like in the original Witten paper or the follow-ups, where you're doing this for a black hole, and the ADM energy is not like the energy above the ground state, it's the energy relative to the background black hole energy. In that case, you let the energy be the full real line, because again, due to the order of limits, you're never gonna get two back reacted, so you just let the energy perturbation be minus infinity to infinity, because it's always suppressed by G Newton. But okay, so there's questions of whether you should do this positive energy projection, when you should do it, whether you can derive it from some other principle. And yeah. But so that's another set of questions. So yeah, I feel like we're fairly over time at this point. So I might want to conclude. I just want to say maybe some other things. So these are all future work directions involved in justifying the construction. I think there's a lot of interesting applications also. If you just take the construction at face value, what else can you do with that? So some things I'm interested in, possibly other people might be interested in as well, is can you apply this to the quantum focusing conjecture? So, or other entropy inequalities. So this is things like, you can start asking about the generalized second law. Can you ask about the Beck-and-Stein bound? So there's some ideas on how you could apply this to understanding some of those things better. You can just use this independently of the gravity. You can use this as a regulator for quantum field theory. And so there's some interesting ways that you can just take the cross product as a way to regulate your theory. We were kind of alluding to that, where we said just take, you see the divergence in this observer entropy. And so there should be, I have some upcoming work that kind of talks a bit about that. So possibly that'll be out soon.
Can you just say one more word? Regulating what sort of quantity?
Like entanglement entropies in quantum field theory, yeah, in particular. Yeah. So we see that it gives a finite entropy. So can you make sense of that? Can you use this as a useful regulator in quantum field theory? Unfortunately, we didn't have time to get to this, but it's the question of other backgrounds. In particular, trying to compare other backgrounds. And just to mention that there's some interesting new ideas in this Witten background independent algebra. So there it's really trying to understand how do you compare like the big part of the entropy, the A over 4G, between different backgrounds. And you have to, some of the algebraic ideas are here useful, but you do have to, add additional parts to it. So just the von Neumann algebras themselves don't seem to be sufficient there. You have to come up with a different way to describe different backgrounds algebraically. And I would just generally mention certain holographic applications. Holography is one of the best models we have for quantum gravity. And so we could definitely use this as a test bed to try to see these algebras explicitly. The original Leuhäuser and Liu paper, really, they got these emergent type 3 algebras from quantum, or from holography. So it's definitely a test bed for understanding new things. Okay, with that, I'll conclude the course. Thanks a lot to everyone here and for people joining online. It's been a lot of fun, so hopefully you all learned something. Yeah, and so we'll finish with any final questions and discussion. So thanks a lot.
There's a question. I just lost my screen. Maybe let's answer live. So Pim, would you like to speak?
Sure. Can you hear me?
Did you unmute?
I thought I did.
Well, yes, the audio is coming through. It's just kind of muffled.
Okay. I'll assume you can
I
understand
accidentally
me.
said
So
it was answered and it's not. I'll ask the question for you.
Okay.
The de Sitter static patch construction for type 2-1 algebra, where there's an observer with a geodesic world line,
Yeah.
to which you gravitationally press your operators, makes me think of the de Sitter holography approach,
Mhm.
where the holographic plate is on the observer world line.
Okay,
Could you comment on whether you think there's a reason for this? Thanks.
well, reason that, I guess I don't know exactly the proposal you're referring to. I know that in de Sitter holography, it's a little more confusing than in ADS holography. And a lot of times either you're trying to define a holographic map on either the horizon of the static patch, but then that horizon is also tied to a choice of an observer worldwide. So I'd say it's a lot of these ideas, specifically with the observer and the introduction of that, are motivated from the de Sitter case. Perhaps you can use, if there's a precise proposal for the de Sitter holography, you could maybe use this as a test bed. Can you take a certain semi-classical limit of this de Sitter holography in order to get, some type 2 algebra and talk about generalized entropies there? So yeah.
Pranav said that he could hear the participants speaking, but we couldn't, so maybe our speaker was muted.
Oh, we might have been muted. Sorry.
Can you
about
hear
that.
me? Can you hear me right now?
Yes, I
Yes,
can
now
hear
we
you
can.
now. Yeah, thanks.
Okay, good.
Please, the speaker.
Okay.
Looks like there's
I have a.
tweet.
Sorry, Professor, were you saying something?
No, I think it was your chat comment that I was about to look at. Go ahead.
Okay, so I have a question and a comment. So the question is, in these assumptions, I don't think you mentioned the fixing of the location of the horizon, sorry, fixing the location of the boundary, the gauge fixing. So does that play any explicit role in these derivations?
Yeah, I think it does in the details. My go-to statement about that, so first of all, these are assumptions, not exactly axioms, so they're sort of a framework of what I think you need to assume, but I'm not claiming a rigorous proof. I would usually put that into this assumption A1. I think these questions about how you fix the subregion really are about how you identify the algebra. And so even when there's these perturbative gauge, linearized gauge transformations can sometimes affect how exactly, for the case of just the gravitons. So I would just classify that as part of what you're trying to solve. When you identify the quantum field theory algebra, you identify a commutant, and that you can associate the commutants in a way that resembles Hogg duality, where the primed one is also associated with the causal complement. So yeah, I would say it's roughly in this set of questions.
Well, the quantum field theory algebra is identified by imposing the constraints in linear order, right? But the gauge fixing constraints, as I understood them, were applied at first interacting order, for consistency with the idea that you wanted to impose all constraints in this commutational sense at first interacting order, and then the ones which are and you handle all the ones which move the boundary by using this boundary gauge fixing. So
yeah, so in some sense, well, I should just mention, there's a duality between gauge fixing and imposing constraints. Like if you fully gauge fix, you shouldn't have to impose constraints. So somehow, yeah, okay, part of it, yeah, okay, maybe these are not all discretely overlapping assumptions, but yeah, so it's the way we set it up is we had these extra observer and ADM and Hamiltonian things that just weren't part of the construction of the local algebras. And we said that there are, as you mentioned, constraints coming from consistently coupling them to the theory as well. So yeah, so perhaps, I don't know, if you come up with a way to eliminate the observer explicitly from the description, you get an intrinsic one, you can unify all 3 steps or something. So okay, yeah, so I don't know if that was a question or a comment at that point.
okay, that was the question. The question was, did you make any explicit use in your calculations of the gauge fixing of the fixed area condition?
Well, the fixed
It didn't
area,
look like you did.
at the end of the day, yeah, these entropy formulas, yeah, just being able to, consider order 1 fluctuations in the observer energy, not order 1 over root G Newton, and the statement that the entropies are finite, you would have issues with, I think, interpreting some of those formulas if you're not, in particular, fixing the area at the order that we were. Because at the end of the day, we wanted something that was finite, in the G Newton to zero limit. And so that was, you need to fix the area of fluctuation to be ordered kappa squared, so order G Newton.
Okay.
Yeah.
So then the comment I was going to make related to Steve Carlop's question from earlier about the fact that the issue of it being impossible to construct an observer out of quantum fields in the de Sitter patch because of this lack of modular invariance.
Okay.
So the thing I was going to say about that is that first of all, that may just be a technical glitch for the de Sitter case, as we were discussing the other day. It may not apply to finite
Yeah.
subregions, so it may just be like an edge case that you don't have to worry about in general. But if you
Sure.
do want to worry about that case too, when you think about constructing an observer out of quantum fields, that seems like a notion which would, like, if you have a specific model for an observer, it would only make sense on a subspace in the first place. So maybe the appropriate condition is that you consider the algebra of observables such that the matrix elements in a particular subspace are invariant under the modular of this particular Bunch-Davies state.
Okay.
And this might not be
Yeah,
known.
okay.
That's just a
Okay.
suggestion that I'm making.
Okay, yeah. Okay, maybe we should discuss more, but yeah. There's definitely. Okay, I don't want to try to do it too much live.
Sure.
But yeah, thanks for the comment.
Okay, let's see. Anyone else? Well, looks like that's it. I would like to thank Antony for everything you put into teaching us about this. And I appreciate all the questions and participation from the audience. And thank you very much.
Okay, thanks everyone.
Thanks, Anthony.